Well done. So let's look into a question from miscellaneous category, right? This question is kind of interesting because it connects bits and pieces from here and there, and kind of really test your thought process. Not very difficult, but definitely worth trying. An aircraft is flying at flight level 350 at Mach 0.81. Let's write the parameters down. Meanwhile, you can take a pause and read the entire question at your discretion. So the aircraft is flying at flight level 350, right? Mach number is 0.81 with a headwind component of 125 knots. So you can see in the previous question we had a negative wind component and given as headwind component, and here headwind component is given as 125 knots. So necessarily should not matter to you. As long as it's a headwind component, it goes from the TAS and you get a reduced speed as your ground speed, right? And the conditions are ISA, and the temperature outside is ISA plus 13 degrees Celsius. What is given here is the static air temperature, or the OAT. The flight distance. Now let's look at the basic parameters of your flight. The distance is 1750. Now I need to kind of highlight this. Kilometers. Be very, very careful with the unit because the unit can kind of shatter you out. You will be exactly on track doing the same steps you have practiced and completely surprised to see that your result is nowhere close to the options, right? In such cases, unit is something which you can always think about and recheck. So one of the techniques that I use is to kind of carry with me the unit so that at any given point of time I find a clash. It's quite easier to detect and correct. Perfect. Now let's look at the rest of the question. The average fuel consumption is 5950 pounds per hour. This is the point where the question takes a different and interesting turn. We have the fuel coming into picture. So unlike in the previous flight planning questions, we have fuel in this particular question. It doesn't make the question a lot different than that you think, but it's definitely a bit off route from what we have done so far, right? So the fuel consumption is 5,950 pounds per hour. Again, a unit definitely worth noting. Total fuel reserves required are. So let's look at the fuel reserves here. So in your general navigation, you have a separate section and separate set of questions dealing with fuel calculation, and they do ask a fair bit of questions from that topic, where they kind of ask you the total flight fuel to carry, given flight fuel, the contingency, alternate, all those different fuel parameters. Here, the fuel reserve, the total fuel reserve is given as 9% of the burn of fuel. Now let me put this in inverted, because burn of fuel, if you've gone through payload, you will know that is same as your flight fuel. So that is your flight fuel. So I'll be taking an entirely different session on payload, the mass and balance part of it. But just to complete the discussion here, flight fuel is the fuel taken that can take you from point A to point B. Just that. No reserves and no additional considerations there. Perfect. So here the fuel reserves is 9% of the burn of fuel, plus they have asked you to add an additional of 100 Imperial gallon. Now this is nothing but the UK gallon. Another unit that is worth noting. Alright, so you can see that the unit of volume is kind of given in association with unit of mass, which is pounds. So you can kind of guess the conversion is going to happen here, right? You have mass and you have volume, and if you want to kind of interrelate them, you need specific gravity. And look at the question, specific gravity is right there, 0.805. That's it. Let me just write it down again. Specific gravity is 0.805. So we will see the connection between mass, volume, and specific gravity in the form of a derivation later in the class in the regular sessions. But for now, specific gravity is a factor. It's very similar to density connecting mass and volume of a fluid. Right. The amount of fuel that should be on board the aircraft at brake release is what are you supposed to find out. So the brake release, basically you're lining up for takeoff. Right. You give power, you release the brakes slowly, and the brake release part of your flight. And the fuel that you carry over there is the entire fuel for the trip, except your taxi and starter fuel, which you have already consumed behind you. So you're asked to find out the entire fuel that you should carry when you're in line for takeoff, so that you can comply with whatever given the question, the rate of fuel consumption, the reserves required, and the wind component given. All right, so let's see here. So the whole idea here is to find out the fuel at brake release point. Right? Now, this will definitely include your flight fuel. Let me write it as FF plus, and that is definitely going to involve the reserves, the total reserves, which in the question it is given as 9% of burn of fuel plus 100 Imperial gallons. And this is all you need to find out. Right? Now the catch here is to find the flight fuel. To find the flight fuel, you basically need the flight time, and if you get the flight time, that's it. You multiply that with fuel consumption, which is already given in the question as 5950 pounds per hour, and you will get the fuel to be carried. Look at the options here in this question. The options are all in pounds, and therefore the unit which we are looking at basically is pounds. So if you can actually convert everything into pounds, and that should help. So flight time into fuel consumption is going to give you the flight fuel. And the next catch is with the total reserve. So total reserve is basically the flight fuel, which is the burn of fuel, reduced to 9% of it, so 9% of burn of fuel. So again, you have to find the flight fuel from flight time and fuel consumption, plus you have 100 Imperial gallons there. Remember, the flight time and the fuel consumption is definitely going to be in pounds because your fuel consumption is in pounds, and you're trying to add with Imperial gallon here, which is not possible. That means that you have to convert the Imperial gallon to pounds. Right, so we can do a basic conversion and you can convert that, and once that is done, you add all these things together, and that is the end. So let's first find out flight fuel then. That's step number one, is to find the flight fuel. Alright, perfect. Now, to find the flight fuel, as I told you before, we need the fuel consumption, which is there in the question, multiplied with flight time. Right? The fuel consumption is right here, 5950 pounds per hour. Into flight time. So here we need to now find the flight time. So just a basic speed distance time equation. Time is equal to distance divided by ground speed. Now remember, we're looking at distance in nautical miles here, divided by, and therefore the ground speed is going to be in knots. Let's look at the distance here. The distance is 1750 kilometers. Now that is something which you have to be really careful about. Let's convert the distance of 1750 kilometers to nautical miles. It's half a kilometer, almost, very close, right? But let's find it precisely using our CX3. So we know that we need to go into the unit conversion tab, and in the unit conversions tab for distances, type in the kilometer value and then press convert unit and find out the corresponding value in nautical miles. Let's do that. It's 944.902 nautical miles. That's it. Let's put this value of 944.902 straight here into the flight time equation here, 944.902 nautical miles divided by the ground speed. Now to find out the ground speed, we need true airspeed, and we also need the wind component. And the question, we have a wind component of 125 knots. Therefore, that goes from the true airspeed. Now, how do you find the true airspeed in the question? Now, see how the question is kind of branching. This is where the question is taking the second interesting turn, where you bring the Mach number into the picture and kind of find out the true airspeed, right? So let's look at the Mach number equation. At any point of time, if you feel like I'm going a bit too fast, it's a video, just take a pause, go back and see it again, and then continue from where you stopped. So Mach number is equal to, it's the ratio of true airspeed to local speed of sound. And we know what is the equation for local speed of sound, right? That is 38.905 root of temperature. And remember, temperature is in Kelvin. It's more like the absolute temperature over here. Now, the catch again. Now let's go back to a bit of met knowledge here. See how the question is kind of tracking all the way. It's taking a completely different route now. We have to find out the true the temperature, outside temperature, and that is not given directly. Instead, they have given you the flight level as 350 and the outside temperature in terms of the ISA temperature. So the deviation is 13 degrees and it's ISA plus 13. So with 13 degrees ISA deviation, your outside air temperature is going to be your ISA temperature plus 13 degrees. Now the whole idea is to find out the ISA temperature at flight level 350, right? So under ISA conditions, be very careful about the fact that the lapse rate of 2 degrees Celsius or 1.9 degrees Celsius per 1,000 feet will continue only up to 36,090 feet or 11 kilometers. That's the ISA hypothetical value. So be very careful with that. Since we are considering ISA values, we have to cap the lapse rate at 36,090 feet and then make the minus 56.5 degrees Celsius temperature constant all the way up to 20 kilometers followed by inversion. So you know all those things, the basic Met knowledge. So here the flight level is 350, it's below 36,090, so we have lapse rate to consider all the way up to that height. Therefore, the temperature, ISA temperature at that level, 15 degrees Celsius, which is the mean sea level temperature under ISA conditions, minus, I'm taking 2 here, you can take 1.98, that's fine, into 35 for every 1,000 feet. So 35,000 divided by 1,000, and that is 15 minus 70, which is minus 55 degrees Celsius. So minus 55 degrees Celsius, this is the ISA temperature at flight level 350. Now what we need is the outside air temperature, which is having a deviation of 13 degrees, and therefore the outside air temperature is minus 55 plus 13 degrees Celsius, which is minus 42, which is right here. All right, now this is in degrees Celsius. To put that in the Mach number equation, we need to convert that to Kelvin, and so let's find it out. Temperature in Kelvin is equal to minus 42 plus 273 to 31 Kelvin. Substituting this value for temperature in the equation here, let's find out the true airspeed. Straight true airspeed is equal to Mach number into local speed of sound. So Mach number is given the question as 0.81 multiplied with local speed of sound is 38.95 root of temperature in Kelvin, which is 231, and that is going to be 479.51. 479.51 knots. What we need is the ground speed. So applying, right, that's the true airspeed, 479.51 knots. Now look back at the equation for flight time here. What we need is ground speed, and what we have, the true airspeed. So we have to apply the headwind component, which is given as 125 knots in the question. So applying 125 knots of headwind, you know, the headwind kind of goes from the true airspeed to get the ground speed. So 125 knots. So ground speed is equal to 479.51 minus 125, which is 354.51. So you can see I am kind of carrying the options, the decimals with me throughout this question, and you will realize that if you round off lavishly in between, your answer might be a bit confusing between the options. Alright, so make sure you carry forward the decimals as much as possible, use the answer function as much as possible. Perfect. We have the ground speed here. Once you have the ground speed, apply the ground speed to this equation and you will get the flight time. Distance is already 944.92 nautical miles. So let's find out the flight time, which is distance of 944.92, that's in nautical miles, divided by, you have the ground speed right about 354.51, and that's in knots. You can see the units are kind of in line. Let's find out what the flight time would be. That's 2.66 hours. Not making it to the so the flight time is 2.66 hours. Now the whole idea of step number 1 is to find the flight fuel, which is fuel consumption of 5950 pounds per hour multiplied with flight time, right? So let's find out the flight fuel. The fuel consumption is 5950 pounds per hour multiplied with the flight time is 2.66, and that's again in hours. The units are again in line. Let's find out what the answer is, and that is 15859.28 pounds. So the options are in pounds, and for that reason we are trying to retain the unit pound. Now having the flight fuel with us, we can now find out the reserve, because total reserve has a flight fuel component in that, right? So step number 2 is to find out the total reserves, right? Now total reserves is equal to 9% of flight fuel, which we have straight from here, plus an additional 100 Imperial gallons, which is same as the UK gallons of fuel. Now you can see we are trying to add flight fuel, 9% of which is in pounds, with 100 volumes of fuel. So it's mass and volume. So basically we need to make the unit same, and as I said, since the options are in pounds, we would like to retain the answer in pounds. Let's find out what 9% of flight fuel would be first. That's the first part to determine. So 9% of flight fuel will be 0.09 times 15859.28, and that's 1427.33, and that is in pounds. Now let's find out 100 Imperial gallons in pounds. So before that, let's go to a short note here. Specific gravity, I'm not going into details of that, the theory of which I do take in my regular sessions. I'll try uploading it once I cover those. Specific gravity, you can consider it as mass, but remember the mass should be in kilograms, divided by volume, liters. The volume that we have here is in Imperial gallons. So first thing first, you have to convert Imperial gallons into liters. So let's do that here. So 100 Imperial gallons, we can use your CX3 and we can convert these to liters. That's 454.6. Once you can navigate to your unit conversion tab and go all the way down to volumes, you can enter 100 in Imperial gallons or UK gallons, and you can hit the convert unit button and you can navigate to liters. Perfect. Now once you have the volume in liters, to find the mass in kilograms, you have to multiply this with specific gravity. Let's do that now. So multiplying with specific gravity, which is 0.805, you'll get 365.96. Now it's very important to understand that this is in kilograms. What we need is in pounds. You can again navigate to the unit conversion tab, and then you can go all the way down to weights, and under weights you can enter the value in kilograms, and then you will be getting it in pounds as 786.96. So that's it. The pound value is 786.96. So once we have both these in pounds, we are good to add to find the total reserve. Let's find out what that would be. Two 214.29 pounds. That's the total reserve. You're asked to find out the fuel at the brake release point. Step 3. Fuel at brake release point is equal to the flight fuel which we have plus the total reserves. Flight fuel is 15859. So flight fuel is right here, which is 15859 plus total reserve is what we just found out as 2214.29, and all these are in pounds, so we are going to add, and that is 18073.57 pounds. The total fuel at brake release point is 18,073.57 pounds. Let's go back to the options now. So we have the value around 18,000, and therefore Charlie is the answer. To begin with, we can see we had good number of conversions, converting kilometer to nautical miles, imperial gallons, all the way to pounds, which in itself involved multiple conversions. Right? We also had to introduce Mach number equation, temperature deviation, and lapse rate concepts in between over here. Specific gravity comes into picture. So you can see the basic fuel calculation is also there. So it's kind of rich a question. So try doing this, and definitely it should help you in kind of mastering few concepts together.